Hello, hello. Hopefully everything's good. Yeah, seems fine. Not too bad. Today we'll be going through the revision seminar for 2801, 2901, of course, stats. And this part is going to be based around things like convergence, estimators, and hypothesis testing. I'm Ronald. I'll be handling the first part of convergence, and the rest is going to be handled by maybe a minute or so. Yes, so May asked, we are going to be uploading the slides afterwards. So, and of course, this will be recorded. So anything you miss, you can come back to if you need to. So don't worry about that. You're not missing out on anything. All right. So first topic is going to be about convergence. And this is maybe what an example question might look like. Basically, we're given a sequence, usually denoted by xn. In this case, they gave us the density function for xn, which is 2n times x to the power of 2n minus 1. They also gave us a domain for x. And how do we know that this is a convergence question? Well, generally they use the arrow symbol to show that it's convergence. Then they give you a specific letter, maybe a D, a P, sometimes an AS, an L to the power of P, and so on. And this letter just tells you what kind of convergence they want. So let's start off with the most important one, which is going to be D. So just a couple questions. We don't have any past paper solutions for 2901. Generally, most of the content is pretty relevant for both. Usually, the difference between the higher and lower is that the higher consists more of proof, and proofs are testable. So I think usually just like pay attention to everything. That will be a lot better for you and everyone else, right? So the first thing is we have a sequence of x1, x2, and so on of random variables, and we say that they converge in distribution to a final limit x if the CDF of xn is equal to the CDF of x as n approaches infinity, right? And we generally denote this as x arrow x with a d on top, which means the sequence xn converges in distribution to our limit x. So the good thing about convergence is usually the convergence is to a single number, right? And this is much easier to deal with. Basically, it would be something like this. F of x is going to be equal to 1 if x is equal to 1, and then it's going to be 0 otherwise. So it might look something like this. Maybe in this case, there's a 1 here, and then the rest is going to be 0. Something like this. So from here, the first thing we want to do is we recall that our convergence in distribution requires us to find the CDF of the sequence and then the CDF of the limit. So that's what we'll do. We'll first look at the CDF of our converging sequence. In this case, we're given the density, so we know to get capital F of x, we need to integrate. Usually it's from minus infinity to x. In this case, we know that x ranges from 0 to 1, so we actually start with 0 and then go to an x. We calculate this integral. It's pretty simple, it's just power rule. So we get x to the power of 2n from 0 to x. And of course, this is just x to the 2n. Now, what we notice is that when x is in between 0 and 1, we see that the limit of our capital F of x, which is the limit of x to the power of 2n, is actually 0. And the reason is because if we have a number which is between 0 and 1, let's say half, and we put it to a power, let's say maybe 2, we see that a half times a half would make the number smaller, right? If we increase the number by 3, we're taking this number and halving it again, and as we halve it and halve it and halve it, it gets smaller and smaller and smaller, and if we take the limit, obviously, the end result is that the number we get is 0. So now we'd like to calculate the CDF for capital F of x, where it's 1 when x is greater than or equal to 0 and 0 otherwise. So we discussed that the CDF might look something like this. So the probability is 1 when it's equal to 1 and it's 0 everywhere else. So the CDF, which is the accumulation of probability, might look something like this. It's going to be 0 until we get the value of 1, and at the value of 1, it's going to jump to 1 and continue onwards. Right? Pretty simple. So our goal is just to show that our xn has a CDF which matches this when we take the limit. And the way we do this is we find the actual value of the CDF at 1, which we can do by integrating from 0 to 1. We use power rule and sum the numbers, and then we should get a 1. And we know that since 1 is just a number, taking the limit as n approaches infinity, it's going to still have it be 1. So what we've shown is that for the range 0 to 1 of x, it's going to be a f of x, which is equal to 0. And then if x is equal to 1, then f of x is 1, right, for xn. And what we see is that this actually does match up with our CDF, right? So we can say that the CDF of xn as n approaches infinity is actually equal to f of x. And this is the condition that allows us to say that xn converges in distribution to 1. Not too bad. So here's a second question. Instead of having a D, we have a P, and the P stands for convergence in probability. So this is something you might notice with convergence. We have a sequence, and we want to show that this limit is somehow equal or approximately equal to a limit that we have. In this case, we have a sequence of xn as well, and a limit of x. We can say that it is convergent in probability if the probability that the difference between xn and x being greater than epsilon is 0 when the limit is taken. We consider this to be when a sequence is convergent in probability. So that might be a bit of a handful. Although Leibniz said in his thing, don't worry too much about it, I think it's still good to know. So it's just the probability that the difference between xn and x is greater than epsilon being 0 as the limit approaches infinity. And of course, it's denoted with an arrow and a P on top. So, same thing here. We want to show that xn approaches 1. So, a good way to start is just looking at the actual limit. And what we see is that this limit can be, for example, represented by a number line. So maybe xn minus 1 has this number line, we want to make sure that the absolute value is greater than epsilon, right? So maybe let's say this is epsilon. So if the absolute value is greater than epsilon, that means we have a value which is greater than epsilon. We could also have a value which is less than minus epsilon, since these values an absolute value which is greater than epsilon, right? So that's what we've done. We've just shown that our thing right here is equivalent to xn minus 1 being greater than epsilon, or xn minus 1 being less than minus epsilon. And of course, we can take this one, put it to the other side, so that we have xn in focus. And then we have this and symbol, which we can split up into two different probabilities. The reason is because we see that these two branches are separate, right? So since there's no overlap, they're independent of each other, and so we can treat these probabilities individually. So the first thing we need to notice is we have the probability that xn is greater than 1 plus epsilon. We know that this isn't true because x has to range between 0 and 1, and so since this value is greater than 1, it's outside of this x range, which means the probability that this happens is 0. Now we're going to look at this probability right here, and the way I'm going to look at it is we first know that the CDF is given by x to the power of 2n from our last question, and we can consider when epsilon is in between 0 and 1. And why do we do that? Well, the reason is because we're looking at the probability that xn is less than 1 minus 0. 1 minus epsilon is in between 0 and 1. And we see that this is actually just equivalent to our CDF, right? The CDF just represents the probability that xn is less than a given value. We can sub in our 1 minus epsilon into this equation right here, and we get 1 minus epsilon to the power of 2n. And from the same argument, we know that a small number to the power of an infinity is just 0. So we can say that this limit is equal to 0. And you might be saying, hey, we define epsilon to be greater than 0. So what happens if it's outside of the range that we set right here? Well, let's say that epsilon is greater than 1, for example, right? This is the remaining possibility for epsilon. Well, that means 1 minus epsilon is less than 0, right? Since this is outside of the range that xn can be, we know that the probability that xn is less than 1 minus epsilon in this case is 0, since obviously xn can't be smaller than 0. So that's pretty much how we've shown that the limit as n approaches infinity for the difference between xn and 1 is being greater than epsilon is 0. Just to recap, what we've done is we've just taken this limit, split it up by what it means, and then we've looked at each individual probability and made sure that for each case we've shown that it's equal to 0. And obviously, a 0 plus a 0 is 0, so we've shown that our limit right here is 0, so we can conclude that xn converges in probability to 1. So we have some other forms of convergence, specifically converging in almost surely, which means the probability that the limit as x approaches as n approaches infinity for xn is equal to equal to x being 1. So that means that we have this limit of our random variable being equal to the limit random variable having a probability of 1. And we have another type of convergence called LP, and this is the expected value that xn minus x to the power of p is 0, which just means that the expected value of xn minus x being 0, which essentially implies that xn approaches x. And for the first case, we denote this as an arrow, and then we write an AS on top for almost surely, and then we have an arrow and LP on top to show that it converges in LP. So why do we need to know this? Well, essentially, we have different types of convergences because they represent different types of strengths. So generally, convergence in distribution is the weakest out of every single one. And we say that the convergence in probability is stronger than the convergence in distribution because if we know that something converges in probability, then we know that something converges in distribution. And we don't know that the other way around. And we also know that almost sure and convergence in LP, both of them are stronger than P, which means if we know that a sequence is convergent almost surely, then we know that it's convergent in probability. And if we know that it's convergent in LP, then we know that it's convergent in probability. And the other thing is, if we know that something's almost surely, we don't actually know whether it's convergent in LP or not, and vice versa. So we now get to a question, and we essentially have 48 uniform distributions from 0 to 1, and we have x bar, and the bar generally denotes a mean. So the way they do it is they just add up every single distribution and then divide by 48, which is the number of distributions that there are. And then they tell us, hey, use central limit theorem to compute that x bar is greater than 0.55. So the first thing we need to know is, what is central limit theorem? Well, central limit theorem basically says if we have an n amount of random variables, which are IID, independent, identically distributed, then they have a mean of mu and a variance of sigma squared. We can say that the mean, the sample mean, asymptotically approaches a normal distribution. So what that basically says is, as we have, when we have a large amount of random variables, their mean or their sum is going to be normally distributed. I also said that their sum would be normally distributed, and the reason is because we see that xn bar is actually just their sum multiplied by 1 on n. So since we know that 1 on n and their sum is approximately the normal distribution with mu sigma squared on n, we see that when we multiply both sides by n, we get that the sum is also normally distributed by a mean of n mu and a variance of n sigma squared. So what we've shown here is that for a large n, the mean and the sum are normally distributed. Generally, we write it like this, where we have the mean minus mu over sigma over root n being approaching or converging in distribution to the normal distribution. So the way we can get this from our thing right here is essentially just multiplying both sides by this sigma on root n, and then adding this mu to both sides. So if we multiply both sides by sigma on n, we get x n as a mean minus mu, which approaches the normal distribution of 0 sigma squared on n. And then we can add both sides with a mu, and that gets us a mean of mu, because adding a constant would shift a distribution over to the left or to the right. And something else that you might notice is that when we multiply both sides by this constant right here, we actually see that this value is squared, and the reason is because the variance of ax is equal to a squared times the variance of x. Which is why when we multiply a constant to some distribution, the effect is squared on the variance. So now that we know what central limit theorem is, let's use it to compute this probability that the mean is greater than 0.55. So the first thing to do is we notice that each individual distribution is a uniform from 0 to 1. So we can use this information to first find the mean, then find the variance to find the sigma, right? And then we can use central limit theorem to show that since 48 is a relatively large number, the mean minus mu, which is a half, over sigma on root n, which is a 12th, over 48, is approximately equivalent to a normal distribution with mean 0 and standard deviation 1. And based on this, what we can do is we recognize that the probability that the mean is greater than 0.55 can be turned into the normal distribution. And the way we do this is we take away the mean on both sides, and then we divide by this constant right here. And then we notice that this is equivalent to the normal distribution z, right? And we essentially just calculate this number to be 1.2. And based on maybe a z table or a output from R, we can show that this probability is 0.115 and so on. We also have something called the weak law of numbers and the strong law of numbers. Basically, what it says is when we have a bunch of random variables, the sample mean converges to the true mean. And this convergence is, in probability, the strong law of numbers is the same convergence, except it's almost surely. So we just had a question. How did we get the variance and the mu? So in this question, the way we got the variance and the mu is if we check the table for a uniform distribution, we know that the parameters are 0 and 1. So since A is 0 and B is 1, we can sub it into the values in the table. And for example, the table says mu is equal to 0 plus 1 on 2. And that's how we got a half. And there should also be a formula for the sigma and how you would get that in the formula sheet that you get during your exam. So, what does this mean in practicality in the larger law of numbers? Sorry, a law of large numbers. Basically, you can think of it like this. When we roll a dice, maybe the first roll might be a 6. Maybe the next 2 rolls might be a 6, right? The sample mean is currently 6. Obviously, this is not the actual mean, which would be 3.5. But as we keep rolling more and more dice, maybe once we've rolled 1,000,000 dice, it's going to be really close to the true mean of 3.5. Maybe when we roll 1,000,000,000 dice, 1,000,000,000,000 dice, it's going to be even closer. So that's essentially what it's saying. As we take larger samples, the sample mean approaches the true mean. This is important because we use this as a trick to be able to show whether, for example, an estimator is consistent, which we'll see in an upcoming part. But for now, we just need to know that the law of large numbers exists, and yep, we can get to one of the applications of central limit theorem. And it's the fact that we can actually use it to approximate the binomial distribution. Why is that? Well, the reason is because we know that the binomial distribution is just a sum of Bernoulli distributions, right? And we know that from central limit theorem, a sum is approximately equivalent to the normal distribution, right? So let's derive this. Let's say that x1 all the way to xn are Bernoullis with probability p. Then we know that the mean minus the mu, which is p in this case, over the variance of a Bernoulli which is p times 1 minus p over root n, is convergent in distribution to n with mean 0 and standard deviation 1. And this is true from central limit theorem. Now, what we realize is we have the mean, which is equivalent to 1 on n with a sum of xi. What we know is that this sum is actually just x, which is the binomial distribution, right? So what we do is we just take this 1 on n, and we can multiply the top and bottom by n, and this gets rid of this root n and gives us this root n, and then we get an n over here to turn it into np, and then we can say we can replace this n times mean to become the x right here. So what we've shown is x minus np over root np times 1 minus p is actually convergent in distribution to the normal distribution. So that's basically what it's saying. It's just saying we can take the binomial distribution and then we can turn it into an approximation through normal. So we also have something called continuity correction, and you can kind of think of it like this. The way we use normal distributions is generally we have a binomial like this. Sorry about that. Maybe something like this as our binomial distribution, and we approximate it through a normal. Generally, how we use the normal distribution is we find the probability that maybe, for example, if this is 3, that x is greater than 3. And then, as we might have seen in a previous question, we can transform this into something like z being greater than some value. But what it does is, in the normal distribution, we take this middle column, right? And then we find the area in this curve. But then what we notice is that in a binomial, we use kind of like a bar graph, right? So the probability doesn't start in the middle, it actually starts over here. Which is why to correct it, we start half value earlier. So this is just a way to correct continuity in this case, as the name suggests. It's just a way to convert between discrete and continuous graphs without losing this half bar of probability. And so that's why generally we add a half or we take away a half. In this case, we have a normal distribution and a couple columns. If we want to find, for example, if this is 2 and the area under this curve, we actually add a half so that we can make sure that we're including this chunk of probability from this column. So here's an example of how we use binomial distributions, and we see that we have two theaters which are competing for the business of 1,000 customers. We want to assume that the customer chooses between the theaters independently and are indifferent. Then we also want to assume we want n to be the number of seats that each theater has. The question says we need to find a condition in terms of n such that they guarantee that the probability of a particular theater turning a customer away because the theater is full is less than 1%. So we want to find the probability that any particular theater is full being less than 1%. And the way we can do this is we can actually model x to be a binomial distribution. In this case, the parameters are n is equal to 1,000 and p is equal to half. The reason is because every customer is one of these slots in our capacity, right? And we have 1,000 customers in total. And since they're indifferent between the two options, that means that they have a 50% chance of going into either theater. So what we notice is that binomials will either give us a 1 or a 0 usually. So the 1 represents them going to a particular theater, which is why this binomial represents the number of people from the 1,000 that go into one of the theaters. So our goal is to show that the probability that the amount of people that want to choose a particular theater is being greater than n is less than 1%. Because the question wants the probability that a theater has to turn away a customer to be less than 1%, right? So this only happens if the people that choose one of the theaters is greater than the capacity, which is x being greater than n. How do we do this? Well, we can essentially just look at each case, right? Let's say if x is greater than n, then we have the case where x is equal to n plus 1. X is equal to n plus 2, and so on until x is equal to 1,000. So that's kind of what we do in this case, right? We've calculated that for some value of x, this is the probability that our capacity is going to be equal to this x value, right? We're calculating this for n plus 1, n plus 2, all the way to 1,000. And by summing it up, we get the probability that x is greater than n. And we want to make sure that this is less than 1%. So what we notice is that we have a 1 minus a half here, and since this is actually just a 1, right? 1 minus a half is just 1 half. We can take this, and then put it into one term of a half to the power of 1,000. So this is our final condition. It's a sum from x equals n plus 1 to 1,000. for n choose 1,000, choose x times a half to the power of 1,000, and we want to make sure that this has a probability of less than 1%. So our next part says we have to explain how a binomial distribution can be approximated by a normal distribution. So the first thing we need to notice is that our end goal is to find what n is, right? But this isn't so easy, and the reason is because we have 1,000 minus n plus 1 terms, and so we essentially have this really big equation, and it's going to be filled with factorials and things like that, right? Because 1,000 cx is going to get transformed into something like 1,000 factorial over x factorial times 1,000 minus x factorial, and so on. And this is just really hard to solve. So instead, the way we can do this is we can make n be in terms of a normal distribution, right? Because binomials can be approximated with a normal distribution, and that allows us to find the probability of x being greater than n much easier, because instead of having to, in this graph, count up every single bar, we can just have a normal curve and then use something like a z-table or maybe a R output to be able to find this probability. So this is the formula before. We can, given that x is our binomial distribution, know that x minus np over root np times 1 minus p being convergent in distribution to a normal distribution, and use this fact to find out this probability. Well, the first thing we do is we minus np in this case, right? So n is equal to 1,000 and p is equal to half. So that gives us np of 500. And then in here we have root 250 to represent root np 1 minus p. And we do that to both sides because that means that this term then becomes a normal distribution with mean 0 and standard deviation 1. And then this becomes the value that we want for a probability of less than 1%. Well, we know that from central limit theorem, this is equivalent to a normal distribution with mean 0 and standard deviation 1. And what that lets us do is we can use this information. So in this case, the question has actually given us an R output. We see that we have a Qnorm. Q stands for quantile. So it has a couple parameters for the normal distribution. The first one is that we want a p of x where x is less than some value, let's say smaller x, right? This being equal to 0.99 in this case, right? So this is what it represents. This represents the actual probability that we want, which is 0.99. Then the 0 represents that this normal distribution has a mean of 0, and this 1 has the meaning that this normal distribution has a standard deviation of 1. So these are the parameters of our normal distribution. And the value we get right here is actually the x value right here. So what this says is, for a probability of 99%, right, in our normal distribution, this x right here, which is 2.33, this probability sum is going to be 0.99. Why is this important to us? Well, we're trying to find values of x greater than some value of x, right? Well, since we need this to be 1%, we know that we can take this remaining part, which is a 1%, which allows us to use this value right here. So, of course, since we want to get a probability of 1%, we use the top result. And from our R right there, we've figured out that for a probability of 1%, we would need an X value of 2.33. And previously, we found out that to be less than 1%, we require this as our X value, right? So we've essentially just gotten this equation, and based on our value, we can then solve for n, which gets us a capacity of 537. So what we've shown is that if we have an n of 537, then there is a 1% chance that we have to turn away a customer. Otherwise, 99% of the time, every single customer will be seated in the two theaters. So we now have our delta method, and basically what it states is if we have yn that converges to a normal distribution, then for any function that's differentiable, g of yn is also normally distributed. That's pretty much it. So generally, this will be denoted as having the function g be applied to the yn and our theta right here, and then being divided by the absolute value of g dash with our theta. Let's look at an example. Generally, we'll have a sequence such as xi, where I is 1, 2, 3, all the way to n. And also the fact that they're independent and they are Bernoullis with probability p. And then we have yn, which is equal to this, which is 1 and n times the sum, i.e. the mean, right? And we want to show that yn minus p times root n is equivalent to this. Well, this looks a bit complicated, but not to worry. It's actually just a application of central limit theorem. We know that yn is a mean, right? And we also know what the distribution of x is. So we can use central limit theorem, where since xi is a Bernoulli of p, we know that mu is just p, and the variance is p times 1 minus p. And if we sub it into our equation right here, we get something like this, where we have yn minus p over root p 1 minus p over n. And this is equivalent to n0, 1. Well, if we multiply both sides by this value right here, which is the sigma, we get left with y n minus p over 1 on root p, 1 root n, and this is equivalent to n 0 p times 1 minus p. And the reason is because the variance of root p 1 minus p times, let's say, z is actually just this constant squared, which is p 1 minus p times the variance of z. So now that we have this part, we just need to recognize that this is actually just a coefficient of root n, which is in front of what we have in the numerator. Pretty simple. Now here's a bit of the harder part. Generally in this question, we've shown that this is true, which is actually the first condition of our delta method, right? We need to show that yn converges to a normal distribution. And that's what we've done here. Now, we notice that we have yn, but we have a function applied over it, right? In this case, the function is g of yn being equal to yn times 1 minus yn. So we get that just by differentiating it, right? Let's say it was in x instead, so we get a clearer view. We can simplify this to x minus x squared. So if we differentiate it, we get 1 minus 2x. So that's what we get right here. And why is this important? Well, since we know that yn is convergent to a normal distribution, we know that g of yn is g to p of g dash p, which is 1 minus 2p. And we know that this is convergent to a normal distribution. So, very simply, we can multiply both sides by this right here. It'll get squared since it's a constant in front of the variance, right? And then we just take this and turn it into a coefficient. And that's pretty much our evaluation of this right here, right? We've just applied delta method and we've essentially shown that since yn is convergent, this differentiable function g is also convergent to a normal distribution. So that's pretty much it for my part, which is convergence. We'll now be going to estimators and their properties, and this will be led by Bruce. Led by Bruce. Led by Bruce.
Alrighty, so you just heard me listen to Ronald handing over to me, but yeah, thanks Ronald. I'm going to go over the next few parts, so just on estimators and also hypothesis tests. This is more of like the part of the seminar where we talk about like applying stats to solving problems with the distributions that we've been talking about. Cool. Alright, so estimators. So what is an estimator? We've talked about distributions with parameters. So for example, the normal distribution has two parameters, the mean and the variance. Right, so the whole point of like an estimator is essentially what it says, to estimate one of these parameters. And what an estimator is it actually maps from a bunch of realizations of the random variable. So I mean, we've seen this kind of stuff before, right? We have a bunch of distributions that follow a bunch of variables that follow the distributions. And so given n realizations of this random variable, how can we map that to something? So one simple example is a mean, right? So if you take the mean of these random variables, then intuitively that should somewhat resemble this number mu over here. So that would be one example of an estimator. So formally written out, you've got a bunch of random variables with a PDF. And any estimator is some real valued function of those realizations of the random variables, and it maps this to, you can write it as g, and usually it's denoted with a hat, so theta with a hat on top. The thing about estimators is they have, well, since its purpose is to estimate the parameter, we can kind of evaluate them by some key properties that they'll need to have. Yeah, so just first of all, to clarify something, the estimator is a random variable, right? So like, if I'm trying to estimate, say, the mean height of the entire population, and I take a sample of like n people, and those n people are all really like short, they're like 1 meter tall. Well, then my estimator is going to be kind of wrong. It's going to be 1 meter, even though the average height is not 1 meter. But my point is that, like, depending on the actual values of x1 down to xn, you get different values of the estimator. And so it itself is a random variable because it's dependent on these random variables. right? And so it'll have its own probability distribution. And usually you can determine that from the distribution of the other random variables, right? And so simple example is the one I just talked about. So the mean of a bunch of normal random variables, or even if they're not normal, we know from what Ronald's just talked about, the central limit theorem, that estimator is going to be approximately normal. Okay, cool. So with that in mind, we can talk about the expectation of the estimator. So bias is just equal to the difference between the expected value of the estimator and like what it's trying to estimate. So you can imagine you want this thing to be pretty close to 0. In fact, we call something an unbiased estimator if the bias is equal to 0. Cool. All right, so let's do an example. Okay, so we've got a discrete random variable, and it's got probability mass px, and it's got a finite space, which means it can only take certain values. We've got our n samples. They're all independent, so this is often a property given to us. They're independent and identically distributed because they follow that same distribution. And this sign over here, remember the hat refers to an estimator of that quantity. So you've got an estimator of P of AJ, which is just, if you recall, the probability of getting AJ. So I'll write that out. The probability that X is equal to A, to AJ. Okay, so we're trying to estimate this, and the first thing they want us to do is show it's an unbiased estimator. So whenever you're trying to show that anything, you need to compute the bias, which means you just take the expectation of the estimator. In this case, you've got this thing on the right. You want to somehow take the estimator of 1 on n times the sum of this expression. Okay. Just a notation thing if you've not seen this very much. This fancy little I is an indicator function, and it refers to whether or not xi is equal to this thing. So whether or not these two things are equal, right? So I'll just write it out formally, but the indicator function is equal to 1 if it's true, so 1 if xi equals aj, and then 0 if not, basically. Okay, cool. And you can already see, well, if something's either equal to 1 or 0, what distribution will that follow? Bernoulli distribution, right? So Bernoulli. Cool. My phone just turned off. Very cool. 1 second, sorry. Okay. All right. Yeah. Okay. So first step of these kinds of bias questions, just apply the estimator to the expression you get. All right. So just literally write E followed by the brackets, and then you'll hopefully get like 1 mark at least, right? But anyway, okay, so you write it out and then you can expand it, right? So when you're doing expectation, you can take constants out, and you can also take sums out, right? So like the expectation of a sum is equal to the sum of the individual expectations, okay? So we've gotten 1 mark already, right? Anyway, okay, so like this thing over here, the expected value of the indicator function, as I said, the indicator function, a Bernoulli random variable, right? It's equal to 1 if xi is equal to aj, and 0 if not. Right? And so with the Bernoulli random variable, the important thing is how likely is this? What is the probability of this happening? Well, by definition, that is equal to P of aj, right? Because when is xi equal to aj? Well, that has probability P of aj. Right. Cool. And so you can do the next step to simplify. I'll just skip this part. But basically, I'll just write it out. The expectation of this thing is equal to 1 on n times this expectation. And you replace this with Paj, and you get 1 on n times n of those, and that gives you Paj. Okay. Cool. The next step of the question was, just to finish off, so to make sure you get like the answer to the question, right? So you calculated the expectation. The estimator has expectation equal to what it's estimating. So bias would be this minus that equals 0. Okay, sweet. And so that's an unbiased estimator. Alrighty, so now we're looking at the variance. So the second part of the question was to calculate the estimator is itself a random variable. It also has a variance. And to calculate the variance, you just go back to the expression we had before, right? So variance of 1 on n times the sum. Remember, when you take constants out of variances, you have to square the constant. So to take this outside the bracket, you need to square it to get 1 on n squared. And then because these indicator functions are independent, because all of the realizations are independent, so xi is independent, you can write the variance of the sum as the sum of the variances. So again, you can take the sum out, okay? And then you think, okay, and so same trick as before, we've got the sum of n things that are all the same, so that just multiplies by n, and then you just cancel out the n squared on the bottom with the n on the top, and you get 1 on n, okay? Just in case, so this is what Ronald was talking about before. It says dragged because I've recently dragged it to my desktop because I heard Ronald talk about that formula sheet. But yeah, like the whole point is that you can check out, if you forget, the Bernoulli random variable has this mean and variance, you can just check it out. So mean is p, and variance is p q, and in this case q is just equal to 1 minus p. All right, sweet. Alrighty, so estimator variance. We just talked about this, but like the whole point of this slide is just, do we want the variance to be large or small? Well, if your estimator is returning like different values every time that are wildly different, that's not ideal. We want the variance to be small, basically, because if it's small, then the value it produces will be reliable. Okay. Sweet. And just one more definition. So we refer to standard error of an estimator as the standard deviation, which means it's just a square root of the variance. Okay. And sometimes you want to estimate this standard error. Like, okay, I'll just give you an example. So like if you take, like just the previous example, right? Like the variance of the estimator is equal to this. Well, if you actually want to estimate that, so let's just say I give you a bunch of values of x1 down to xn. Let's say you want to estimate the variance. Well, you still don't actually know what this value is, right? Remember, this thing with a hat is the estimator, and the thing without the hat is what you're actually trying to estimate. So no one actually knows what this is, right? So when you're actually trying to tell someone, for example, like what is the variance of this estimator, you wouldn't tell them this thing over here, right? Because still you don't actually know what P of AJ is, right? So what you would actually do is, okay, I'll give you the standard error. Well, first of all, standard error is a square root here. Yeah, standard error is a square root, and still this is not good, right? Because no one knows what this thing is, so this helps no one, right? So what you want to do is you want to replace the actual thing, the actual parameter, with the estimator itself. Because the estimator you actually have a value for, right? So you would say, okay, I'm going to quote the standard error for you. I'm going to sub in my actual parameter that I estimated, and then I'll give you this. Cool. So that's what this slide is saying. It's difficult to estimate the standard error of an estimator because the variance is often a function of the parameter itself. So what you do is you substitute in your estimate for the parameter. So this line over here means that. So you just replace all the thetas with theta hat. Okay. Cool. All right. So one more property, and then we can do a really cool question. Yes, MSE is mean squared error, and that's the expectation of the difference between our estimator and the actual parameter squared. Okay. So it looks pretty similar to the other things we've seen before, bias and variance. And in fact, you can actually express it as a sum of the bias squared and the variance, right? And so MSE kind of combines bias and variance, right? We know we want bias to be low in magnitude, and we want variance to be low. And so MSE kind of combines these two concepts. And if your MSE is low, that means that both of these things must be low. So sometimes when you're comparing two estimators, you can just calculate MSE and say, well, the one with the lower MSE is surely better. Okay. Sweet. Cool. All right, let's go into some questions that involve a lot of the properties that we've talked about before of distributions in general. Okay, so bunch of first of all, identify the distribution, uniform 0 theta, and we're trying to estimate theta. Okay, and two estimators for theta are equal to this thing over here and this second estimator. Okay, so first thing to show that both estimators are unbiased. And as in the previous question, you just want to calculate the expectation, calculate the bias, and to show that that's 0. Okay. Cool. So let's do that. It's quite an involved process, but let's look at the first one. Well, the max of a bunch of random variables we've done before, and we know how to calculate, for example, the p. U is equal to the max. And what we'll do is we'll calculate the expectation of this guy, and then the expectation of this estimator will be that times n plus 1 on n. Okay. So hopefully we kind of remember how to do. Hopefully we kind of remember how to do this. But you would go through the CDF, because the CDF is defined in terms of probability. So probability of u being less than a certain number u is equal to the probability of the max being less than the number u. And if you remember from maxes, you can actually split this up, because if the max is going to be less than u, well then all of them need to be less than u. So you can just split it up as a product. Oh. Cool. Yeah. So because they're independent, you can just split it up. And what happens is each of these is uniform 0 theta. And so let's go back to the question. Uniform 0 theta, is it here? It is not. But that's okay, because if you a nice way to remember the CDF of a uniform distribution is, well, the uniform distribution is a straight line, right? The PDF is a straight line. So because CDF is just an area under the curve, you can just calculate it as a rectangle, right? So this is x, or in this case u. Well, the height is going to be 1 on theta. So the total area up till u is just equal to u divided by theta. And so it's the product of n of these, which is equal to u on theta to the power of n. Cool. All right, so you've calculated the CDF, and we know that the CDF is pretty hard to use, just in general. Because you can't calculate expectations using the CDF usually. So what you do is you try to differentiate this to get the PDF. Yep. Yep. And then you calculate the expectation by your standard procedure. So expected value of u is equal to the integral. Okay, yeah, my n's sometimes look like u's. It's a common problem. Yeah. Evaluate from 0 to theta, because that's our range. And then just take all the constants out and divide it by theta to the power of n. That turns into u to the power of n plus 1. And you can imagine you substitute that in, you get this. Yeah, it looks a lot like a u. You can see the issue, right? Bunch of cancelling out, and you get n on n plus 1 times theta. Okay. Alright, sweet. So that's almost there, because now we want to calculate the expectation of that times n plus 1 on n. So it's just equal to n plus 1 on n times that. You can see it's cancelling out, it just becomes theta. So the final line you would write is just bias of this thing is equal to theta minus theta equals 0. Okay. Sweet. yeah, second part, calculate the estimator of this one. That's a bit easier because it's the mean, so I will just, so yeah, these slides are going to be uploaded afterwards, but basically, this is the solution if you want to read through it in your own time. Yeah, the second part is a lot easier. So we've done expectations of means before, right? So theta equals n times the mean. So you just take the expectation of that. And what you would do is expectation of the mean is actually equal to the mean of one variable. That's a common property we use. And if you forget the mean of the uniform distribution, that's okay because you can check it. Yeah, so this is what Ronald did before. So like if you've got a uniform AB, then the mean is going to be equal to half of the sum of them, right? So that's kind of intuitive, right? Because if you define between A and B, then it's going to be somewhere in the middle, which is like the arithmetic mean. Okay. Sweet. Okay, so in this case, we've got 0 plus theta divided by 2. And so what that means is that the expectation of this thing is just equal to twice that. And yeah, unbiased. Yay. Cool. Alright, so the next question is which of the two estimators is better? Okay, so remember, better is kind of ill-defined, but if you've got two variances with two estimators with the same bias, then the only thing that matters now is the variance, right? Because MSE is equal to bias squared plus variance. So it actually ends up being that the one with the lower variance is actually better. Okay. Now, let's do the variance of the second one. So variance of 2 times the mean is going to be equal to 4 times the variance of the mean. Remember, we square any constants when we take them out of the variance operator. And so variance of a mean, hopefully you remember, is equal to 1 on n times the variance of 1 on n times the variance of one given variable, which is equal to 4 on n times, again, you can check out the formula sheet, but basically a half times beta minus a, not beta, b minus a squared. So in this case, it's going to be a 12th times theta minus 0 squared. Okay. So yeah, that's where this comes from, and you get 1 on 3n times theta squared. Alright, so for this one, it's a bit more involved. I won't do it on a separate sheet because it's very involved. But basically what you do is the variance of this thing. First of all, you can very simply just take the constant out and square it. And that way you've reduced it to just doing the maximum. Okay. So variance of u, which we calculated before. So remember, u had this little thing. If you're worried about what this thing is, it's another indicator function. So it's equal to 1 or 0. It's equal to 1. It's equal to 1 if if u is in that interval. So if u is between 0 and theta, and 0 if not. Alright, so basically what this is saying is that this is only defined, or it's only non-zero between 0 and theta, otherwise it's just 0, okay? So what you would do is just do the variance, right? So hopefully you remember that the variance is equal to the expectation of u squared minus the square of the expectation. Yeah, and so you can just calculate both integrals. So expectation of u squared is equal to this all times by u squared. And then we've already calculated this before. It's equal to n on n plus 1 times theta. And basically, both of these are just integrals. You just do them, and you get something that looks kind of gross, right? It's just another massive fraction, right? So you can do that, and then what you do, the final step, is just to compare the two variances. Yeah. So just remembering what the other one was. I said that, but then I've actually forgotten. So what was the other one? 1 on 3n times theta squared. The other one is 1 on 3n times theta squared. And so the question is, which one is actually bigger? Well, generally speaking, you want to compare it when n is very large. So you don't really care about constants, you just care about limiting behavior. This one is like n divided by n, basically 3 n's, right? So n on n squared, n cubed, sorry, which is approximately equal to 1 on n squared. But this one is actually just 1 on n. So the question is, which of these variances goes quicker to 0? Like, we've kind of done this like before in graphing, right? Like, not in stats, but in like other areas of maths. This one just decays faster because the power is bigger. So which one is better? Well, it's going to be this one, right? Cool. Don't worry too much about this notation if you're not sure what it means. All it means is just 1 goes to 0 faster. And so this one, the one with the smaller variance, is the better estimator. Okay. Sweet. All right. Another property of estimators. So an estimator is a consistent estimator if it converges in probability to the actual parameter. It's just terminology, like Ronald went through probability. Yeah, and you can show using Chebyshev's inequality that if the MSE approaches 0, then it's consistent, right? So that's often a very easy way to show something is consistent. You can just calculate the MSE and hope it approaches 0 as n approaches infinity. Okay. Cool. Another thing that becomes quite important later is an estimator is asymptotically normal if the difference between this and the actual estimator divided by the standard error. We've seen this kind of stuff before, right? So the mean minus mu divided by sigma on root n, or you'll see this a lot later too. Don't worry too much about it, but it's very common, right? If you do, it's called kind of like z-scoring, right? Like you subtract the mean divided by the standard deviation. If that approaches n01 in distribution, the estimator is asymptotically normal. Okay, cool. Alrighty, so let's walk into like actual techniques for calculating for using estimates and also for calculating good estimates of random variables. Okay, so yeah, basically this page is all about how you can estimate a random variable, but like remember, an estimator is a random variable, so you're always going to be like wrong, right? You won't always have this thing, right? Estimator equals the actual number. Okay, so what you want to do is, in statistics you can never say anything for certain, right? You can never say like I did an investigation, now I know that the average, okay, I did an investigation, now I know that mu is equal to 5. Right, that's not really something you can do because you're never going to be sure, right? Anything can happen. Like for example, let's say human height is normally distributed at like 1.7 meters. Variance of something, I don't know. But I don't even know if this height is right. I don't think it is. But anyway, the point is, let's say we have human height distributed here, and as I said, like you could like survey like 1 million people, and they all have height like 1 meter or something, right? Your estimate is going to be 1, but that's still possible, right? Because the normal distribution goes on forever. So the whole point is that like you can never be sure of what a parameter is equal to. So that's the motivation for a confidence interval. Before I go into like the technical details, basically a confidence interval is just an interval of numbers such that you can say this for certain, right? The parameter lies within here with probability. Often it's 95%, right? So 95% of the time I do this investigation and I come up with these lower and upper bounds, theta will lie over here. Because you can never say theta is equal to something, but you can say it lies in this region likely, like with a certain probability. Okay, that's like our end goal. That's what it says here. So you've got a bunch of samples, so x1 down to xn, on a random variable where it has this PDF determined by a parameter. Yeah, and we specify what's called alpha It's often called alpha, which is like a level of like error that you're comfortable with. And you say that the interval, like L and U, stands for lower bound and upper bound. We say that it's a 1 minus alpha times 100% confidence interval for theta if the probability of it lying there is equal to 1 minus alpha. Okay. Cool. My phone keeps on shutting off, so I might have missed some questions. Right, doesn't seem like it. Cool. Alrighty, so yeah, and 1 minus alpha is called the confidence coefficient. Okay, so there's an example over here, which is like, you've got a sample from the normal distribution. You know what sigma is? Then a 1 minus alpha times 100% confidence interval for mu is equal to this, okay? Let's not look at this. Let's instead try to derive it, okay? It's a good example because like a lot of these confidence interval questions require you to come up with the confidence interval from like first principles, okay? So our end goal is to say mu lies between two numbers with probability 1 minus alpha percent, okay? So what you often start with is by looking at the distribution itself. And the first step is called basically taking this distribution and transforming it. So x, remember x is given by normal mu sigma squared. Transforming this random variable to something that is free of any parameters, right? What I mean by that is you want to basically get rid of mu, okay? And the reason why you want to get rid of mu is so you can reduce x to something that's well known. For example, if you can reduce it to n01, like we know everything about the n01 distribution, right? So we know, remember we have those probability tables? We also have like R outputs. So, for example, we've like probably seen this quite a bit. If you've got the n01 distribution, then like something like 68% of the values lie in this black region, right? And Ronald walked us through like normal quantiles, right? Like you can always, if you need like a certain percentage to be over here, so you need like 95% over here, then if you need 95% to be over here, you can find the exact numbers, or not exact, but the approximate numbers you need up at the top and at the bottom to get 95% there. So this is starting to look like a confidence interval, right? So if you want 95% to lie within two regions, then what you need to do is somehow reduce this to a normal 0, 1 random variable, and then we'll somehow use these numbers over here. So the numbers such that within them is 95%. Okay, so let's do that. So we've got x1 down to xn. And so you can imagine the natural thing to do is to take the mean. Okay, so the mean has n mu sigma squared on n. Hopefully we've seen this before. You take the mean, you divide the variance by n. Yep. So now we've got something that's still not quite free of sigma and mu, but that's okay. Because what can you do? You can z-score, right? You take away the mean. Now this is turned to 0. And then you divide by the standard deviation. This turns to 1. Okay. Alrighty. So the mean minus the actual mean divided by this thing follows n01. And so that's perfect, right? Because I said our first thing we want to do is reduce this to something where we don't have to worry about mu and sigma. We just have a clean distribution where we know like everything about it. Okay. And so what we do next is we say, okay, we've achieved what we wanted, right? We've got a distribution that doesn't have the parameters in it. Okay. Now what we want to do is you want to say this lies between two other numbers with probability, and you refer to what you actually want. So in this case, we're doing the generic version. So often we'll have alpha equals 0.05, and then in that case, this is a 95% confidence interval. But we're just trying to derive the generic expression for it. So this lies between two numbers with probability 100 minus 1 on alpha percent. And a very common technique is to think, okay, so we need one number up here and one number down here, such that we've got 100 times 1 minus a lying over here. So the fraction is 1 minus a. That means what's left over, the non-black stuff needs to be alpha, right? It needs to have probability alpha percent. So, sorry, 100 alpha percent. So you've got to have alpha on 2 up here, alpha on 2 down there, okay? So for example, 95% confidence interval, you need 2.5% up there, 2.5% down there, okay? So hopefully you remember that, like, we have these things called normal quantiles. Either you can use the table, or you can use, let's do some R. I know everyone loves R. Basically, to find this number, you're effectively solving for the quantile, and the quantile is defined in terms of how much is less than a certain value. So we've got 2.5% up there. We need 97.5% down there. So it'll be Qnorm. It's like 0.7975. And you don't have to specify any parameters, because by default it'll do 0, 1, and that should give you something like I think it's 1.96. Okay, so this will be 1.96, and so basically what you're saying is this thing I've just constructed. So the mean, I'll just write it up again. Needs to lie between 1.96 and minus 1.96 with probability, and I'll write this again, um, 95%. Okay, I should have done the generic version. This is the 95% confidence interval, which is good. But let's do the generic version. We say, if we're trying to do a 100 times 1 minus alpha percent confidence interval, then it needs to lie between we write the quantiles of the normal distribution like this. So 1 minus alpha on 2. And lies between that and this. And the normal just to clarify, this is the 1 minus alpha on 2 quantile of Z, right? So for example, in this case, it's a 97.5% quantile for it. But because the normal distribution is symmetric, this lies between, you can actually just write it like this, and it'll be between that and minus the same thing, okay? Sweet. That's really cool, but it doesn't answer the question, right? The question is, can we write mu lies between two things such that the probability is 100, 1 minus alpha percent? We can, right? Because you can just rewrite this and make mu the subject. So, personally, there are lots of ways to do it, but I would just take the negative. It's going to be the same thing because it's symmetric. Let me know if you're not following, by the way. And then you would just multiply through by this, then add that back, okay? So it'll be, I'll just write it again. That plus Z 1 minus alpha on 2 times sigma on root n, okay? Cool. Yeah, and so the final way of writing the confidence interval is this thing, okay? So the mean minus this quantile times sigma on root n, and then that plus the same thing. Okay. All right, sweet. So I think that's cool. But basically, you just want to show that the confidence interval is defined in this form. There's a derivation over here, but that's basically the process we use. Okay. I won't go through this. You can read it through if you want to download the slides afterwards. Yeah, cool. All right, so the next thing we want to talk about is the t-distribution. It looks really scary, but all it is some kind of distribution. It looks a bit like the normal distribution, so it's also symmetric. I don't think you don't need to memorize this. It's just kind of there for completion. But it looks kind of like the normal distribution. But the difference is normally if you just divide something by the actual standard deviation, you get a normal distribution. Okay. But sometimes you don't have the standard deviation, so you use what's called the sample standard deviation. It's equal to 1 on n minus 1 times the sum of the deviations. Then that, if you replace it with that, you get something that looks like the normal distribution, but it isn't quite the normal distribution. It's equal to the t-distribution, and we call it with degrees of freedom n minus 1. Okay, so the t1 distribution is the t-distribution with degrees of freedom 1. In this case, we've got degrees of freedom n minus 1. Cool. All right, so you can probably guess that like a very similar confidence interval for it looks basically the same, right? Except instead of sigma, you've got s, which is our sample standard deviation, and instead of the normal quantiles, you've got I'll explain what this means. This is the t quantile, right? It's a t quantile because it's the quantile of the t distribution with n minus 1 degrees of freedom. And also you see the 1 minus alpha on 2 thing again, because we're doing the same process, right? We're saying, okay, it's got to lie between, this has to be 1 minus alpha, so we've got to have 1 on alpha on 2 on the top, alpha on 2 on the bottom, okay? So basically, when you've got unknown variance, you don't actually know the variance, you'll need to estimate it, and that involves using the t-distribution, okay? So it's the same thing, except t instead of normal, and also sample standard deviation instead of the actual standard deviation. Cool. Yeah, so this is a sample mean. This is a sample variance, and that's a quantile of the t-distribution. Okay. Sweet. Alrighty, so another big algebra question. Yeah, we just take it step by step. So they've given us a PDF. They've given us an estimator, but first step isn't even related to the estimator. So like, this question looks really scary, right? But like, you can try to take it step by step and just don't get scared by like the multiple parts. Just try to do it one by one. Okay. So xi squared, that's just going to be, in terms of one variable, would be gamma 1 on pi times lambda. Okay. So this is not even related to estimators. It's just going to be in terms of transformations, right? So this is x. How do you find x squared? All right, so hopefully we can kind of remember that in a univariate case, to take a transformation, you often can use a CDF method, right? Which means you say, okay, I know the probability of x being less than x, but let's do the probability of x squared being less than x. It's going to be the same thing, except let's make x the subject. Yeah, this will be the CDF of x squared. You do the probability of x being less than root x, and that's going to be the same thing, except you sub in, this is just going to be the CDF, except you sub in root x, okay? So I did forget a step here. You have to first calculate the CDF, because we're not given it. Yeah, probability of x being less than x. Yeah, so you just want to integrate from 0 to x of this formula, so 2 lambda t e to the minus lambda pi t squared. Okay, I think that's right. Cool. Alright, so that just becomes a matter of integral by substitution. This becomes e to the minus lambda pi t squared 0x, and you end up getting 1 minus e to the minus lambda pi x, okay? Sorry, x squared, okay? And so then this expression, so the probability of x squared being less than x, is just going to be the same thing, but e sub in root x, okay? Cool. Now it'll just be 1 minus e to the minus lambda pi x, okay? That looks quite familiar, right? So all you need to do is just to show that it follows the gamma distribution. You just want to find the CDF of this gamma distribution and then show that they're equal, okay? All right, CDF of gamma distribution. Will just be yeah, this is where the oh yeah, so they don't actually give the CDF here, so there's no CDF. That's okay, because we can calculate the PDF of this one from the CDF and then compare PDFs, okay? So the PDF is just going to be equal to the derivative of this, so it'll be lambda pi times e to the minus lambda pi. Okay. Yeah, so now we can do the PDF of the gamma distribution. Gamma with 1, I think it was 1 on pi lambda. Yeah, and so that's just going to be equal to the same thing, but we sub in those parameters, so you'll get alpha is 1, of course, so e to the minus x divided by this thing, so e to the minus pi lambda x, all of that times x is 0 divided by gamma 0 times this to the power of minus 1, okay? Sorry, 1. So that'll be the same thing. And so because the PDFs are equal, you can conclude that they're equal in distribution, okay? Sweet, okay, so now we're doing a function of these random variables. So the density function of this transformation, you want to find the density function, okay? So what you want to do is just try to find, apologies, what you want to do is just try to find the distribution of this itself. So when you've got a sum of a bunch of random variables, you can often do that using the MGF approach, right? So MGF approach allows you to sum up independent random variables. So what you would do is let's define u to be equal to this thing. Oh no, sorry, we've got t already. T is equal to pi divided by n times the sum yeah, and so they found the MGF of that. Sorry, it'll be t times t. Sorry, mx of, sorry, I am experiencing jet lag. Okay, mt of t will be exponential of, sorry, the expectation of e to the power of, that's my excuse, jet lag, e to the power of t times t, which is equal to the expectation of, just sub it in, pi on n times t, times this sum. Yep. Okay. Cool. Alrighty, so, yeah, so basically what we do with like sums in an MGF approach is, because a sum is equal to, basically the sum of, if you have a sum in the exponent, you can turn it into a product, so it'll turn into this. You need to just write it all out. And because these are all identically distributed, you can actually just write it as a power of n, so they're all the same. Cool. So yeah, the expectation of this thing is going to be to the power of n. And then the next thing you deal with is this thing over here, the pi on n. What you would do is you would actually just, because now we've got e to the power of x times a bunch of numbers, you can group these all together. Yeah, and so this is actually equal to the MGF, because this is just a constant. It will be the MGF of x times the constant itself. Okay. Sweet. Alright, hopefully that makes sense. So the first thing you do is you break up the sum into product. Then with this extra constant here, you merge it into the t, and then you just chuck it down in the MGF. Okay. And so now we know that the variable itself is x. X itself had the, oh sorry, my bad. It's going to be the sum of x squared, so same kind of approach, but now you have a squared in each of these terms. Yeah, so MGF of x squared, we know the distribution of x squared is gamma 1 on pi lambda, and so what you can do is you can calculate the MGF from this table. So MGF of gamma is, oopsies, 1 divided by 1 minus beta u to the power of alpha. So it's going to be equal to the power of n. So 1 minus 1 divided by 1 on pi lambda times t in this case to the power of minus 1, or to the power of n. Okay, and so that becomes 1 minus pi lambda on t to the power of minus n. So I'm going to check if there are any questions. Yeah, there was a question a while ago. Creating a confidence interval using the t distribution and a sample standard deviation. So it would kind of be the same sort of thing. So like a t distribution and a normal distribution, they're both like statistically rigorous, right? So we constructed them from the definition. The only difference is like to use normal quantiles. So the question is, to use normal quantiles compared to t quantiles, is that exact? They're both like exact strictly, but like this one requires you to know the exact SD. So it's not more accurate, but it does require more information. This requires us to estimate. Estimate the SD. Okay. Sweet. Alright, so any questions about like this algebra, let me know. But essentially you're just subbing in the gamma MGF and putting this in through. Okay. Alright, sweet. So the next thing is, okay, we've got this MGF. They want us to find the PDF, which generally speaking requires us to find the distribution, right? So what is the distribution of this thing? Well, like, it looks pretty similar to the gamma distribution, except the gamma distribution looks like this, right? You've got Sorry, I think I made another mistake. So this should be, because we're subbing in pi on n times t, we need to just chuck that in. So this becomes pi on n times t. The pi's cancel out, but you've still got divided by n lambda, so it becomes n lambda on t. Okay, cool. Alrighty, so we're almost there. Basically, the whole point is this looks really similar to the gamma distribution, because the gamma distribution has an MGF looking like this, right? 1 minus 1 on t times beta to the power of minus alpha. So it looks really similar, except here the two parameters alpha and beta are different, right? Here we've got alpha equals n, and then lambda will be equal to, beta will be equal to 1 on n theta. 1 on n lambda. So you've compared these two, and you've reached the conclusion they're the same, except now we've got that t, it is gamma, except the parameters are given by like these two parameters here, right? N and 1 on n times lambda. Okay. Sweet. Alright, so that's on t. The next question is, can we find the PDF? I'm not going to go through this part, but basically all you do is you just chuck that into the gamma distribution. We know the PDF of the gamma distribution. You chuck those variables in, and then you get this answer. Okay. Sweet. Let's move on to the last question. Derive a 95% confidence interval for lambda. Okay. So generally speaking, you want to use what we just talked about. So t, that's a massive, unfortunately. T is, which we just got, right, is given by gamma n 1 on n lambda. Okay. So if you want to use this to do a confidence interval for lambda, you need to get rid of lambda. Okay. And what they're telling us is we can use, I'll just scroll up. You can use what's called the scale property of this gamma distribution. And what that is basically, if you've got a gamma random variable, then if you multiply x by a number, so xn, it's equivalent to multiplying the second variable by 1 divided by that number. Okay, so multiply by something, you divide the second parameter by that same something. Okay, so that's a bit of a hint, because now what we want to do is take this, somehow get rid of lambda. Okay, so if you want to get rid of this lambda, you need to multiply the second parameter by lambda, which means you do the opposite on the other side. So you do 1 divided by lambda times t is going to be gamma n, and there'll be 1 on n. Okay, sweet. All right, so let's rewrite this on the next page. So t on lambda is gamma n 1 on n. Okay, so that's good. Now we've got a distribution that's free of lambda. Okay, so the next thing we do is we say t on lambda, it's going to lie between two other variables. It's going to lie between these two variables with probability. Remember this step, with probability. I forgot what the confidence interval we needed, 95%. So with probability 95%. Okay, so t on lambda needs to lie between two things with probability 95%. And remember the gamma distribution. Usually for this question you'd use R. You'd say, okay, or they give you the odd output most likely. So you need 0.025 here and 0.975. Okay, because remember we want half at the top, half at the bottom. Okay, sweet. Okay, so this is going to lie between basically these two numbers. Okay, I've written it out on the slides, but basically this thing. Okay, so you take the quantiles of the gamma distribution. This is the R output, so Q gamma 0.025 n, and the scale parameter is 1 on n. Same thing here. Okay. Except with 0.975. Alrighty, so that's going to lie between those two. So the probability of it lying between, so the probability of lambda on t lying between gamma 2 and gamma 1 is going to be 0.95. Okay, and then what you do is you just basically make lambda the subject, right? So remember, what we're after is lambda lies between two things with a probability. So just multiply through by t, and you've got your answer. Okay, so your confidence interval is now just lambda 1t, lambda 2t. Okay, sorry, gamma 1t, gamma 2t. Cool. And you can always just rewrite what t is in terms of what we got before. So, yeah. Sweet. Any questions? No questions. Alrighty, so we have two more things to cover. So MLEs and also hypothesis tests. Let's go through MLEs now. Okay, this is one way of doing a likelihood, one way of doing an estimator. So basically, given the PDF, PDF is like probability, right? It's like proportional to probability. So the likelihood function is the product of all the probabilities or the product of all the PDFs. Okay, and so you can imagine that if this thing is high, that's better. So in this case, you're trying to maximize the likelihood. So if your likelihood kind of looks like, as data changes, looks like this, you want to find this value, right? You want to find the value of theta that maximizes this likelihood function. And if you recall from like finding maxima of things, right? Generally speaking, it requires you to differentiate. The issue with like likelihood functions is they're products, and like products are really hard to differentiate. So what we often do is we take the log likelihood function. We say this is our likelihood function. Take the log of that, and now instead of trying to maximize this, we're trying to maximize the second thing. Okay, so now we turn a product into a sum because that's what logs does. And so when you try to maximize that, it's a lot easier because you just differentiate this, and you just get the sum of the derivatives. Okay. Cool. Hopefully that all makes sense. All right, so that's the definition. So the maximum likelihood estimator is the number that maximizes the likelihood function. And actually, this is equivalent to maximizing the log likelihood function, right? Because if you maximize a number, you're also maximizing its log. Okay. Sweet. So the point at which the likelihood function attains its maximum is also where the log likelihood attains its maximum. So the MLE is also, it can be found from finding the maximum of the log likelihood function. Cool. All right, let's do one example with the maximum likelihood estimator for the Pareto distribution. Okay. So the first thing you want to do is you're given a bunch of random variables, so x1 down to xn, and you want to calculate the likelihood. Okay, so likelihood of theta, so likelihood of alpha, is equal to the product of all of these. So you'll have alpha times x1 to the power of minus alpha plus 1, alpha x2 to the power of minus alpha plus 1, all the way down to xn. Okay. Let's continue this on the next page. Often it's good to simplify. And basically what we'll do is we'll group all the alphas together. Will be n of those, so a to the alpha to the n. Then all of these x's you can combine together as well. So it will be x1 to the power of minus alpha plus 1, x2 minus alpha plus 1, all the way down. Cool. Yeah, sweet. So you can imagine this is quite hard to differentiate. So we'll take the log likelihood. Products turn into sums. So you've got n log alpha plus minus alpha plus 1 log x1 minus alpha plus 1 log x2, so on and so forth. Yeah, cool. And so now the benefit of doing the log likelihood comes in, because now you can differentiate quite easily. You've got n on alpha minus, all of these turn into just log. Cool. So what are you trying to do? You're trying to make this all equal to 0. So this equal to 0 when n on alpha is equal to the sum cool. And so you can imagine that you can just solve for alpha, and that's our MLE. It's equal to n divided by the sum. Okay. Sweet. That's what we want, so we've got the correct answer. Alright, I'll leave you to read this if you want on the slides. Oh yeah, one thing you want to also do, should have mentioned this. So as with like finding maxima in general, it's not enough just to have the derivative equals 0. You also want to show the second derivative is negative. And in this case it's equal to, differentiate one more time, you'll get minus n on alpha squared. That's less than 0, so yes, it's our maximum. Cool. Alrighty, so MLE properties. So the MLE has a number of properties. So one of them is consistency, so it's consistent. It converges to the actual number in probability. In variance, which means that if you actually want to find an estimator for a function of the MLE, you can actually just take the function of the MLE, right? So, sorry, if you want to estimate a function of the parameter, so say the parameter squared, all you do is you just take the MLE and you square it. And that's also the MLE of the square. Okay. Last one is it's also asymptotically normal. So as you go towards infinity, you take the difference between it and the parameter, you take the standard error, and that will converge to n01. Okay. Sweet. Next thing is the Fisher score. So the Fisher score is defined by the derivative of the log likelihood function with respect to theta. Okay. And the reason it's important is because you can actually calculate something called the Fisher information, which is quite important, as the expected value of the second derivative of the log likelihood times minus 1. Okay. We'll go through an example, but the Fisher information is important because if you take 1 divided by the square root of the Fisher information, that gives you the standard error of the MLE. So as you go towards infinity, the standard deviation of the MLE can be calculated from this number. Okay. And if you think about it, like that means that you can actually replace the standard error with the Fisher information. That's going to be asymptotically normal. So you just multiply through by the Fisher information on the top, and you'll get this. Okay. Cool. Delta method. So Ronald went through the delta method as well. But if you take the standard error of a function of the MLE, then because of the invariance property, all that happens is you go from 1 divided by the square root of the Fisher information to the derivative of that function divided by the standard error. And so you can actually just do this thing. Cool. Alright, so find the estimated standard error of this set of random variables, of this MLE. given this likelihood function. Okay, so remember the Fisher information you can calculate first. The Fisher score, the Fisher information is going to be I n theta is equal to the expectation of negative the second derivative of f, okay, of the log. Okay, so that's going to be the expected value of, oh sorry, no, they already gave us the Fisher information, so the standard error will just be 1 divided by the square root of that. And so that means that you can calculate this approximate distribution by doing this divided by the standard error approaches N01. And so you can just multiply through, you'll get, I'll just do it for you as well. So estimator minus the actual parameter approaches N0 theta squared on N. And so you can just add back theta and you'll get N's theta squared on N. You can imagine that because of the asymptotic normal property, you can actually use this to reduce, remember the first step of a confidence interval is to calculate like a distribution that is independent of theta. Well, you can do that over here, right? And so you can imagine that leads to a confidence interval, right? You'll get the confidence interval called a walled confidence interval is equal to the estimator minus the quantile times the standard error, and then the same thing at the top. Okay. So you can see that like once you understand the basic idea of a confidence interval, all of them become pretty relatively easy to understand. Yeah, cool. A fun fact about estimators, which is quite useful, is if you've got an unbiased estimator, the variance is always going to be greater than the inverse of the Fisher information. But if you remember, like the MLE, basically as n goes to infinity, this equality holds, right? So the variance actually approaches this thing. So that means that as you go towards infinity, the MLE is actually basically optimal. Okay. Alrighty, last Fisher information question. This involves calculating the Fisher information. So we've already got the MLE, we've already got the PDF. So let's do the Fisher information. Fisher information is equal to, remember the formula? So expectation of minus the second derivative of the log likelihood. So so log of this. Yeah, cool. I'm gonna check the comments. If any questions. No questions, okay. So yeah, so basically just differentiate this. So expectation of this, just differentiate it at first. So do the first derivative. You can just expand it first as well. So it'll be log alpha minus alpha plus 1 that. Okay, so just do the derivative of that. So you do first derivative is this, second derivative is this, sorry, second derivative is this, so minus, it'll be minus 1 on alpha squared, and this is not dependent on alpha, so it disappears. Yeah, you get expectation of n on alpha squared, which in this case does not have a random variable, so it doesn't have x in it, so you can very safely just write n on alpha squared. Okay, hopefully that makes sense. But yeah, that's the Fisher information. So now the confidence interval for alpha is going to be that walled confidence interval, right? So you'll have alpha, the estimator, plus the square root of 1 divided by the Fisher information, so alpha on root n, times, in this case we've got 90% at the top, 90% throughout, so we need the 5% points, okay? Yeah, so it will be z 0.95, and then the other one will be alpha minus z 0.95, okay? Sweet. Yep, so that's the answer given here. And you can see that we've got like the estimator of alpha instead of just alpha itself. Because remember, like, it's not very helpful to quote the standard error just in terms of alpha because we don't know what alpha is. So you just replace it with the estimator itself. Cool. We'll skip this because it's not actually very common for it to appear in exams. Some years it's not examinable. But yeah, this is something you can look into in your own time. Basically, it extends the Fisher information concept to multivariate estimators. Okay. Alrighty, so the final topic, hypothesis testing. This is a pretty, it's a pretty conceptual topic, but all it is you've got two things that you want to test out, alright? So you've got a bunch of distributions, basically, and you want to see whether, like, everything we've just talked about is about, like, estimating parameters, right? So you've got an estimate for a parameter theta, and you know it lies roughly within two regions. Well, what you want to do is be able to take that concept and use it to make conclusions about data sets, right? And to do that, you need to do it formally and scientifically. So you've got two hypotheses, one which you are basically accepting to begin with, and another one that you want to try to test out, okay? So let's just say a very common example is like biased and unbiased coins, right? So your assumption initially is that the probability of getting a heads is a half. That could be your null. But your alternative might be, okay, so I've been doing a lot of coin flips with my friends recently, and it always seems to be heads for some reason. So you'd say, alternatively, P could be greater than a half, okay? So basically, this is our null, what we accept already. And the other one is what we're trying to test out. And remember, H0 is the null, and H1 is the alternative hypothesis. Okay. Sweet. So the null hypothesis is a claim that a parameter of interest takes a particular value, theta 0. It escaped the bracket somehow, but it should be theta 0. Therefore, H0 has the form theta equals theta 0 for some predefined value theta 0. Okay. And the alternative will take one of multiple forms. It will either be theta is not equal to theta 0, or it could be one-sided. This is called two-sided. But if we strongly suspect it leads in one direction, so it's going to be greater, then we do one-sided tests. Okay. And so the whole point is to see how much evidence we have for H1 as opposed to H0. Okay. Alright, so it's best done with an example. So we've got an example, we're trying to figure out whether toast lands bottom side down more than bottom side up. And you try out 24 trials, so you've got x1 down to xn, and you found that 14 of the times it lands bottom side down, 10 times it lands bottom side up. So you can kind of see why we need hypothesis tests, right? Because simply getting more slices of bread landing bottom side down doesn't mean it's actually the case that it's more likely. Maybe you just got unlucky, right? I paused for a minute because I didn't know whether you would want your toast to land. You probably don't want your toast to drop at all, but anyway, like, maybe you just got unlucky, right? It always just landed by the side down. So the question is this evidence? And to do that, you actually need to do something called formulate what's called a p-value, but we'll talk about that in a second. Okay, so the method is this. Null hypothesis and alternative hypothesis. Okay. Basically, you're trying to answer the question like how much evidence is there against a null hypothesis. So what you do is you take your data, you aggregate it into a test statistic. Often it'll be something like the mean, because the mean is very representative of like where your data is trending, right? And so it measures how far your observed values differ from what you expect under the null. Okay, and so what you do is you calculate the p-value. The p-value is let me do this on a new page. So let's do this example. Okay. Yeah, so, sorry. 14 landed by the side down, 10 landed by the side up. What you're saying is like, it seems like it's more likely that, remember, h0 is p equals a half, h1 is p is greater than a half. So the p-value mentions, this is a really important phrase, I'm going to write it out, the probability of getting a value as extreme as what you obtained, or more extreme. Okay, so extreme is a really ill-defined word, but what I'm saying is that extreme means like something that supports the alternative hypothesis. So in this example, right, you've got 14 landing by the side down. Something as extreme as that would be 15 landing by the side down, because you've got more evidence rejecting the null. Okay, so what you would do is in this case, your probability, so first of all, our test statistic is equal to the number that land by the side down, so the number that land by the side down. And when I say more extreme or as extreme, I mean basically something that offers evidence for this that rejects like the null. Okay, so in this case it would be probability of t being greater than or equal to 14. Okay, so what is the probability that you do this experiment and you get more than or equal to 14 pieces of bread landing by the side down? Okay, that's what extreme means. So I'll write this out. It measures how much evidence there is for the alternative hypothesis under the null hypothesis. So in this example, p-value is equal to this. Okay, hopefully that makes sense. I'll talk more about when this like changes a statistic. But yeah, that's what it basically means. So as extreme or more extreme. Cool. And so you can imagine that the smaller this value is, the more extreme a value you got, right? So if somehow like you do another experiment and you get like 23 landing by the side down, 1 landing by the side up, well then something's up, right? Like the probability is equal to probability of t being greater than or equal to 23, which is very small. And so what you do is you set a threshold. So the threshold is like a number such that if it's less than that number, you will reject the null. Okay, so if p is below our desired threshold, and we call that the significance level, we reject the null and say, okay, something's wrong. The null is clearly very implausible, so we accept the alternative hypothesis. Okay. Sweet. Okay. So you can see the hypothesis test process. Another example you can do is just a sample proportion. What you would do is, in this case, you would do the probability of it being greater than your observed. Basically, under the null, if it is true, then the test statistic, the sample proportion minus 0.5 is going to be normally distributed. So if you got a value of whatever we got, so we got 14 on 24, then the question is, normally this value would be like this, right? Normally our test statistic would follow the N01 distribution. But in this case, we have to see whether this value is very large. So we say, okay, we got 14 on 24, which means we got 14 on 24 minus 0.5 divided by 0.5, 1 minus 0.5 divided by n. What value do we get for that? Well, if that thing is very big, then we will reject it. Okay. Hopefully that makes sense. In this case, we're using a slightly different test statistic from what I said, but the reason why we do this is just to reduce it to a normal distribution, so we can calculate probabilities more easily. But the essential question still holds, right? Sub in the value that we got. So we got a really big value. We got 14 on 24 minus 0.5 divided by this. If this thing is such that the probability of getting something more extreme than that is very small, then we will reject, okay? So let's go through this a bit more slowly. So this is our p-value, okay? If you're not sure, just let me know in the chat. But our p-value is equal to the probability of this statistic being greater than 14 on 24. And so what you can do is you reduce it to the normal distribution and say, okay, the normal distribution tells us that 20% of the time you'll get something more extreme than this. So in other words, 20% of the time you'll get a proportion bigger than 14. So that seems pretty reasonable, right? If only 20% of the time, if we're getting something similar to this 20% of the time, it's not that unlikely. So usually we set our significance at 0.05. It's greater than 0.05. So what that means is we don't have to reject the null. So don't need to reject the null. Cool. Hopefully that makes sense. I'll check the chat just in case there's confusion. Yeah, so Huang asked a nice question. So how do we know if it's too small or too big? Well, the way we quantify that is precisely by using the p-value, okay? So the p-value quantifies how likely you are to get a number as big as this, basically. So you can see that the p-value is the probability of getting something above 14 on 24. So what that means is that if this number is really small, that means that the number we got was massive, right? Because barely any times we do this experiment, we get something as big as that. So you quantify it by doing the p-value, if that makes sense. Okay. Cool. So over here, this level of significance is a threshold. Commonly, we set it to be 10% or 5% or 1%. And the convention is to select 5%. And since in this case, the p-value is greater than 0.05, you don't have any evidence, so you just accept the null. Okay. What number do we compare it to? So the question is, what number do we compare it to? Yeah, so you don't need to compare it to a number, because what you can do is, I think what you're alluding to is a rejection region, which we can talk about later. But there are two ways to do this hypothesis test. A p-value does not involve comparing it. Does not involve comparing. Comparing our test statistic to a number. Yeah, because what you're doing is you're saying, okay, our sample proportion is 14 on 24. I'm not going to compare this to a number. What I'm going to do is going to say, okay, what percentage of the time are we going to get something as extreme as this? So probability of my sample proportion being greater than 14 on 24. Okay, does that make sense? You don't need to compare it to a number. You just say this sample proportion, which is a random variable. The sample proportion is a random variable. What percentage of the time do I get something as massive as 14 on 24? You reduce it to a normal distribution, which is what we did here. So sample proportion minus 0.5, 0.5, 0.5, divide by the standard error. And so it turns out that this random variable only becomes that big like 20% of the time. So yeah, so it's not too big because this probability is larger than our significance level. And so you get, you don't have to reject. Cool. Yeah, it's a good question because it alludes to something called a rejection region, which we'll talk to later. And that does involve comparing two numbers, but we'll see how that goes. Cool. Yeah, hypothesis tests. So this is basically saying when you're testing normal samples, this will be your test statistic. Minus mu divided by s divided by root n. Okay. Yeah, and so what you'll do is maybe I'll just yeah, we'll just do an example. Okay. So daily yield of fertilizer. I'm just seeing if we have much time. I think this is the last example. Yeah, basically the last example. Okay, cool. So let's just read through the question. Ignore this for now if you don't get it. We'll talk about it now. Yeah, let's just talk about this. So daily yield of fertilizer before was 880. And so now we've got new machinery installed. We want to see if it's better. So already from like the English words, you can establish what we're trying to do, right? So the null is the default, so mu equals 880, and the alternative is basically, is it more efficient? So is it greater than 880? So be careful because sometimes you'll get greater than, sometimes you'll get less than, sometimes you'll get not equal to, right? It depends on the wording. If they had said, for example, we would like to know if the new machinery is different or like has some kind of effect, then there'll be mu is not equal to. But in this case, we're trying to figure out if it's more efficient, so we do greater. Okay. So we've got 50 days, we've got a new sample mean, and we've got a sample standard deviation. Okay. So the question is this evidence that the new machinery is more efficient? Okay. And so we're going to use a hypothesis test. No significance level stated, so we'll just use our default of 5%. Let's go. Okay. All right, cool. So, sorry. Cool. Okay, so basically what this part is saying is this is a really good test statistic. So just take the sample mean minus the mean divided by s on root n, and that follows t n minus 1. All right, and it's always good to have a distribution because then you can quantify more extreme and you can quantify the probability of getting something more extreme. Okay, so in this case, what value have you gotten? Okay, so mu is equal to your null, so 880. So basically you're asking if the null is true, then this thing follows the t distribution with n minus 1 degrees of freedom. So the value that we got of our test statistic is equal to 888 minus 880 divided by the sample standard deviation. So what was it? It was 21 divided by root 50. Okay. What you're saying is that if the null was true, then this should be t distributed. Okay. So what number is this? I'll get my calculator out. you'll get 2.69. Okay, and that's T49 distributed. Okay, so what you would do now is you would say, okay, this is a number. Yeah, it's a number. But the question is, how big is this number? And is it a very extreme number? And so you then go to calculate the p-value, right? The p-value is the probability of getting something more extreme than this. In this case, extreme means it's greater, okay? Because you're trying to figure out if it's more efficient. So extreme in this case, so you're trying to figure out if it's more efficient. So extreme equals larger. Okay. So p-value will be equal to the probability that t is greater than or equal to 2.69. And you can use your t quantiles to figure that out. I think it's written here. I don't know what it is. But yeah, using r, you can find out it's 0.0049. And that's going to be far less than 0.05. And so you reject. Basically, you say this is really extreme, so we can just reject it pretty safely. Okay. If the question had been not equal to, let's think about that. Then you'd still have t equals the same thing, so 2.69. But now extreme can be in either direction. So your p-value will be equal to your probability of getting something more extreme in either direction. So extreme in this case refers to the magnitude. So it will be t is greater than 2.69, or another way of being extreme is less than minus 2.69. Okay, and because the t distribution is symmetric, it will just end up being 0.0049 times 2, and which equals 0.98. Okay. The point is that your hypothesis tests themselves determine what extreme means and then determine what p-value means. All right. Sweet. Yeah. So if H0 were true, we would be highly unlikely to observe a t statistic as large, and so we have strong evidence. Okay. But yeah, someone asked a really nice question about like comparing like our test statistic to something else. That's alluding to the idea of a rejection region. Okay, so what you can do is instead of actually finding the p-value, you can find the theoretical, like, okay, let's look at this. So t lies on a t distribution, which is kind of symmetric. And so let's just go back to the original problem. Okay, so I'll write this up. H0 equals 880. Or H0, sorry, mu equals 180, or it's greater than 880. Okay. You can see that like you're going to reject if it's very big, right? But what is the first value for which you'll reject it? Well, if you're going to reject it, you need the p-value to be less than 0.05. So the first number for which you'll reject it is actually the quantile at 5%. Because if you got 5% above it, what that means is that you will reject, your p-value will be less than 0.05. So you will therefore reject the null. Okay? And this is called a rejection region. The rejection region is a set of values for which you will reject the null. So what you could do alternatively is find the value with p-value 0.05, which is a quantile, so t 49.95. And then you could actually compare, so we talked about comparing numbers, you could compare your test statistic to this number. So this number, I'm not sure what it is, I think it's like 1.6 or something. Let's say it is 1.6. What you would do is you would compare it to 1.6. If it's greater than 1.6, you would reject, right? If it's less than 1.6, you would not reject. So that's an alternative way of doing this. So you first choose a level of significance for the test, and then you would find the quantile. And that's an alternative way of figuring out whether you will reject something. Okay. So yeah, oh, that's not too far off. It was 1.676. So you'll reject if it's greater than 1.676. Our observed value was 2.69, which is in our rejection region. Okay. And as such, you reject H0. Okay. Final thing is the power function. Okay. What is a power function? It gives the probability of rejecting the null, given that theta takes that parameter value. Okay. So an example is you've got like mu is less than or equal to 0 versus mu is greater than 0. So intuitively, as your mu gets higher, it becomes more likely that you will get something that supports this hypothesis, right? Because as your actual number of the mean gets higher, then you'll be more likely to observe a big mean, and so you'll be more likely to accept this thing. Okay. That's an example of a power function. I won't go into this too much, but yeah, all of the stuff with like normal probability applies. Like you can calculate this using tricks from before. Lastly, the level of significance of a test is the maximum value of the power function over the viable values in the null hypothesis, right? So the null hypothesis could actually be multiple values. You could be, in this case, it's mu is less than 0. So the size of the test is basically saying, what is the worst case scenario, right? Why is this the worst case scenario? Because the power function is what happens when you reject the null, right? Right? The worst case scenario is the biggest value of the power function over the null hypothesis. Because that means that like the null is true, but you reject it anyway, right? So in this case, the null is less than 0. So the power function would be your probability of rejecting that null. And so if you get a really big value over this region, then that's bad, right? So what you want to do is track all the values over that region and make sure it's kept to a low. So the supremum or the maximum of the values is going to be the power, or sorry, the size of the test. Okay. Cool. We won't go through the generalized likelihood test because it's not as commonly assessed, but you can read through it on the slides. We are running short on time, but basically the generalized likelihood test is a generic test for a hypothesis test, right? All you do is you reject if this test statistic is low, and you actually find out that when you have certain conditions where you have this kind of hypothesis, then that test statistic follows a certain distribution, being the chi-squared 1 distribution, and what you'll actually get is you can calculate the p-value or the rejection region using chi-squared test statistics. Okay, sweet. All right, so I will skip this question. But yeah, hopefully that was helpful. But that's going through basically statistical inference, which is talking about like how you can estimate certain numbers and how you can basically do hypothesis tests using certain numbers. Okay. Yeah. Any questions? Just let me know in the chat. But yeah, that's basically bringing hypothesis tests to a close. What I might do actually is I might do the word test because that's pretty important. So, yeah, I'll do the word test. The word test, as you can recall from our word confidence interval, is sorry for baiting you, by the way. Yeah, we'll do the word test. Basically, the word test is a specific test for MLEs. Okay, so in this example, for example, you've got a word test with alpha equals 1.16 versus greater than. Okay, so you can imagine that the first thing you do is you calculate a test statistic, and unsurprisingly, it's the word statistic. So alpha minus the actual number, so alpha, divided by the standard error, so 1 divided by this, sorry, it would be the Fisher information to the power of minus 1 or 2, Yeah. And so you'll basically say this will follow N01. Okay. Yes, because the first step to doing a hypothesis test is always to find a statistic such that the distribution makes sense. Okay. So basically our test statistic is the world test statistic. And what you would do is you would calculate it. In this case, okay, I'll go through how to calculate it. Basically, you just sub in the MLE, okay? So in this case, you can easily calculate the sum of the logs. You do n divided by the sum of the logs, and you'll get 53.7. Okay, so it'll be 100 divided by 53.7. Okay. Sweet, so you just sub that in, and you've gotten a world test statistic of 6.053. And so basically the central question is, how extreme is this? So check again your hypothesis. It's going to be greater than, right? So when do we reject? When it's big, right? So you want to reject, so your p-value is going to be the probability of the world test statistic being greater than or equal to 6.053, okay? And that's a normal random variable. So you can easily just calculate the quantile of the normal random variable. Sorry, not that. It would be somewhere in R, you can calculate this. It'll be very, very low, basically. Another thing you could do is use the rejection region method. So remember, the rejection region method is basically what is the threshold at which, sorry, I'll just write this out again. So your world test statistic follows a normal distribution. The world test statistic is trying to find, is going to be normally distributed. So you want to find the first value at which you would reject. And because your p-value, your significance level is 0.05, it's basically asking you, what value do we have 0.05 of our values above it? And that's going to be 1.67, I think. But basically, you can use R or you can use your normal tables, and that's going to be a rejection region. And basically what you'll say is, well, our test statistic was way bigger. It was 6.053. And so it has to be in the rejection region. So reject. Cool. Yeah, so that's the world test. Just calculate, you can see it's becoming a bit easier, right? So you can just calculate, like, hopefully it's becoming a bit easier, but you can just calculate, like, the statistic, find the distribution of the statistic, then calculate the p-value, or do the rejection region. All right, so I'm going to check to see if there are any final questions. Yeah, cool. It looks like we're good to finish. Oh, sorry, there's one more question. Yeah, what formula did you use to find probability of z being greater than 0.82 besides RStudio? So there's no method other than RStudio, or other than RStudio, you can use like your normal tables. So I don't have it here, but basically in your exam, yeah, you'll basically get a table, and it tells you for any given value of like z, so maybe like 3.5. I don't know exactly how it's like structured, but you'll get, for example, 3.5 corresponds to some kind of probability. I'm assuming it's quite small. But basically what it means is you've got this probability of getting z greater than 3.5. Okay. Basically it's just a grid, right? They give you a bunch of values and it maps certain values of your probability to probabilities themselves. Okay. I think that wasn't super clear, so I might just search up a normal table. Actually, what I can do is, one second, I can open my laptop. And I will share. Tragically, I can't find it. One second. I'll just find a normal table. But yeah, thanks everyone for coming. I'll just answer this final question. But yeah, if you have any other questions, just let me know. But I'll just I found one on maths is fun. I guess that's kind of useful. Okay, 1 second. Yeah, cool. Maths is very fun, by the way. Okay, so maths is fun. Basically, okay, this is a good table. So basically what they've done is they've put different digits on different axes. So this cell, for example, you can see 0.1 and 0.01. It corresponds to 0.11, but they do it in a grid to make it easier to read. So for example, 0.96 would be 0.9, 0.06. And you go all the way down to here, and this is that value. But what does the number actually mean? It is the probability of the standard normal random variable being greater than that, okay? So if, for example, I need you to find the p-value of a Wald statistic, and the Wald statistic is 0.96, then this is that p-value, right? You're trying to find the probability of it being greater than that, and that's going to be equal to 0.3315, okay? Hopefully that answers the question. Yeah, any other final questions, just let me know. I think I wasn't sharing. Oh, thank you, Tim. I love you too. All right. But yeah, I just realized I wasn't sharing, which is really cool. Wait, sorry. I'll just Okay, give me some time. But I'll just answer the final question. But the seminar's over. Yeah, one final thing. Okay, it's really cool. Alright, basically, I will just say it verbally, but we've released revision sheets for our seminars. You can go to unsw.mathsoc.org, and there's a tab at the top that says revision sheets. But yeah, we've done it for MATH2901 and 2801, and also for 2501 and 2601. So feel free to visit that, and you can download the sheet there. Yeah, cool. I will answer one final question though, and but the seminar's over, and thanks for coming. Cool. Okay, cool. I got math columns, so you've got 0.9 and 0.06. That's just basically a way to display 0.96, okay? They do it to make it look easier. But yeah, basically what it is corresponding to 0.96, you've got the probability of your normal random variable being greater than that, right? So in this case, if you got a Wald test statistic of 0.96, you would know the p-value is equal to 0.3315, right? Because that's basically saying this is the probability of you getting something more extreme than that, okay? Hopefully that answers that final question. Yeah, if there are no other questions, we'll just end at that. And thank you for coming.